Okay, so hi everyone. I think we're live. Let's check the audios. Yep, I am audible, I believe. Yep, welcome to another session. So, today is the last session for this 29 days. Now, we have solved a lot of problems, and also I've given out a lot of problems for homework as well. So, I believe you are already you have already solved them with me. um, if not, like again, I would recommend you to solve all the questions that I have solved, because again, like they are all important questions, and where it comes from interview perspective. And for the homeworks also, try to solve them as well, because I have actually chosen the problems that are like generally asked or that are popular interview questions, and then I've given, right. So in this entire series I have focused mostly on things like dp graphs and trees, because these are like again like these are very important concepts. I've also covered linked lists and other things like greedy algorithms, something like sliding window, and these binary search. Well, so in today we'll be learning about two data structures that we have not covered. That is tries, which is also very important, but again basically we'll be covering tries and dsu. So both of these data structures are very important, but again, like with respect to the applications on interview questions, it's pretty limited. It's not that there are a lot of problems, or it's not very like if they're asked, if you are asked, like it's very common questions as well. It's very common to ask dsu questions or try based questions, but again, like most of these will be of similar patterns, right. So there will not be a lot of variations on these dsu. There might be some variations, but again, like it's more like if you understand what the concept of dsu is, what dsu does. Generally when you get a problem, you will see that that concept applies, and then you actually try to use a dsu, right. So today we'll be learning about both of these data structures by solving problems definitely. So the first problem we'll solve is for try. We'll be learning about try, and we'll see like how to insert and search in a try. So the problem is try, insert, search. It tells that try. It tells about tries. It's used for storing strings and these things. Your task is to use a try data structure and search a given string a. If found, print 1, else print 0, right. So the, a, there, answer, any, by, there, and search keyword is the. You have to output the, because the is present in the string, right. Right, so it is present in the, so, so in the string the, there, by, there. Again, like this gigs output should be 0. So we have to search, right. We have to search in a like we have to search. Basically the problem is you are given a list of strings. You have to search whether a given string is present in this list, right. Talking about try, right, what try exactly is. Try is a prefix matching data structure, right. Try is a prefix matching data structure. Prefix matching, what do we mean by prefix matching? It means that, let's say you have anything, like let's consider string only. You have some string. So before, like in the first part of the string, you have a prefix and then the complete string. So this, any prefix of the string, if you want to match with this prefix of the string, whenever there is a prefix matching problem, try is generally the go-to data structure, right. So whenever there is a prefix based matching problem, you will generally try to use a try. All right. So for example, what are some use cases of try? If you think about the use cases, general use case is called search type ahead, right. Search type ahead. So search type ahead means when you search something, right. Let's say you want to search, let's say cat. So you type ca, and it will give you the recommendations after this. T can come in, or rd can come in card, or tch can come in catch, like this, right. So this is the search type head. So if you see, This is kind of a prefix matching, right? You type in CA and you are returning the list of words that are actually matching, that has a prefix of CA, right? So that is like one of the important problems that try solves. And this search type ahead is like similar to what search engines and IDs, online IDs, these, right? So if you're asked like questions around design a online search engine, right, or design a online some ID in with autocomplete feature, in that case you can use this try to do the search type ahead. All right, so that's about what try it what is the purpose of try. It is used for any kind of prefix matching. Now prefix matching doesn't necessarily mean only for strings, but it can also be for integers. For integers you can actually convert to their binary notations and then do a prefix matching, right? But again, like, we'll not discuss that in details. So let's understand the problem. So or let's understand how a try is created, right? So let's say we have something like this: the man, mango, there, tornado, let's say some of the words are present. So what we create is we have a root node. From here, based on the first character, we will branch out, right? So based on characters, we'll branch out. So here we have T, right? So one of the branches will be going for T. For T, we will have one of the branches and it gives to a new node. We have M. So for M, we will have another branch because the first word is M. And all these, and these are the only two, right? For the first character, T, 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 and M, M, right? So that's how the first. Let's talk about the second from T. So one of the branches will be with the character H. We have again H here, and here we have O. So one of the branches will be O, right? After H, there will be E. There will be one of the branches E. Both of them have E, but here we have RE as well. So there will be R and E as well, right? So every character, as you go through the characters, it will basically form a path in this try, right? Also note one thing: there is a, okay, we'll come to that later, but then there is tornado, right? So TOR, there will be only one, now only one of the strings has TOR, right? So it will be a single path from now. So tor, again nado, it completes here somewhere, right? So again man and mango. So M, we have one child A, and again we have N, we have G, right, mango. Okay, now let's say we are given, if there is there in our string, if there is there in our string, so what we'll do is we'll start from here. Now is there a branch towards T, towards the character T? Yes, there is T. So we'll move to T. So the first character is done. We'll move to the next character H. So from here, is there a character H, branch for character H? Yes, there is, right? This branch is H. So we'll move to this H, and here also we'll move by one place because H is completed. Now see, when we reach there, in this string we have ERE left, right? And we are already sure that we have traveled across TH. So whatever is below TH should contain only the words that are starting with TH, right? After that we have E, so we'll go to E. After that we have R, we'll go to R. After that we'll go to E, right? And we see that we reach the end of the try, so we return that there is one of them. But this is a bit problematic, right? Whatever we have implemented, that is not completely correct. Why? Let's say we want to search for the, right? We want to search for the. In that case, see, when we end at E, we do not know if this is the ending of some node, right? We do not know. So for that, we will maintain a boolean flag for each of the nodes if it marks the ending of a node, right? So here it will be marking the ending, so it will be 1. Here also it will be 1. Rest of the nodes here will be 0, right? So similarly, mango, N will be 1. GO, it ends, marks the end of a mango, so it will be 1. So this marks the end of the words, and now here from 1 we can understand that there is indeed the in the set of strings. So we'll return true, right? So this is how a try is constructed. Now like, this is how the try looks like, and this is how the searching occurs. But now to understand programmatically how a trie is constructed, so we will create a node. Like it's definitely a tree, so we will create a node of the tree. Now the node contains some of the values, right? So first thing it will contain is something like is last node for, or is completion node, is word end, let's call it is word end, right? Does it mark the end of a word? So this is the boolean, is word end. So we'll have this boolean flag, bool is word end, that will be true if it marks the end of a word and false otherwise. And similarly for the next nodes, how many next nodes can we have? So next nodes can be any English character, lowercase English character. How many of them are there? There are 26 English lowercase characters. So the next nodes will be of type node again, node star next, and it will be of size 26, right? So this is how the structure of a node looks like. It contains the boolean, is it the word end, and also it contains pointers to next 26 nodes for each of the characters, right? So what, how do we construct a trie? Let's say we have three characters, right? Instead of 26, let's assume three characters. So we have three characters here. So we see, let's say it starts with a, let's say we are inserting aba. So a, it starts with a, so for a it will be creating a new node. A means the first one, right? B will be the second, C will be the third. So a, for a only it will create a new node. Now from here we see that there is B here. So for B, this goes to A, right? For B we will be creating a node, new node, that is for the middle one. So for B we will create a new node. After this, for A we will create a new node. So ABA is inserted into a trie like this, right? So this is ABA. Let's say we have A C B, something like this, right? So A is already there. Now here we had B, right? Now we want C here, so we will create a new node for C. We'll create a new node for C, and here we want B, so we'll create a new node for B. So this is how we insert into the trie. Okay, now when it comes to searching, let's say we want to search for AB, right? We want to search for AB. How do we search? We start with the first character and we start at the root node. We see if there is a node that that is starting from A, that has A, like is there a node for A? Yes, there is, right? The next of A is there is a next of A. So in that case, A is there, so we'll cross out A, we'll move to the next node that is pointed by A, and we'll go to B. Now here, from here we see, is there a node that is pointing towards B? Yes, there is, right? B, there is a node. So we'll move to this node and we are done with the string. So this is how we actually search on the trie. So let's understand more about this by trying to write the code for this. All right, and let me know if you have any doubts. So this is how the trie looks like, and yeah, this is how you perform the operations. But definitely, like, I think it makes more sense to write the code directly, right? So yep, let's see what is the structure of the trie node. And it is leaf is true if the node represents the end of a word, right? So we have is leaf and we have children, trie node children. Okay, so insert, we are inserting into the trie. So all right. Void, let's call it ins, or we can actually we can do it in a loop format as well, or we can do recursively. Like there are two ways to do it. We can do it recursively or we can do it by looping, right? So for int I, so int current node, try node star current equals to root, right? Try node star current is equals to root. Am I using C++? Okay, so struct try node star this. Now we'll go through the characters. T dot size I plus plus. Now we'll find the ASCII value, right? So index, we'll basically find the index in the next node, like for the given character. So that will be int G of I minus A. It will give the index like A will become 0, B will become 1, C will become 2, like that. So int index is this thing. After that, if card of children, I think it was children, right? Card of children, yes, card of children of index is equals to null. So card of children of index equals to new try node, new struct try node, and get node returns a new try node. Okay, initialize to nulls. Okay, so initialize to nulls will just call get node, right? Node malloc. Okay, so we'll just call get node. So we'll just call get node. Struct try node star get node insert into. Okay, so insert will be, we'll call get node, right? And we'll get the node, and it should be a default node now. Uh, so okay, so card of this and card equals to card of children and x, right? So we'll go to the next node. Now finally, when we come to the end, we'll mark card of is leaf to be true. It is the end of a word, right? So this node represents the end of a word, so it will mark it to be is leaf to be. So what we have done here, again, we are going through all the characters one by one, right? We are going through all the characters one by one. We are finding the index, the next index. So we are assuming that we have already traveled in the try for the previous characters. So for this node, we want to find what is the next index it will be going to. So we are finding the index by finding the like we are converting this to the ASCII value and then mapping it to like 0, 1, 2, like that. So once we find the index, we see that if the index is next node is null at that index, in that case we create a new node, and after that we move to the next new node, right? And finally we reach to the end of the word. So that time we are at the last last node in the try where this word has ended, so we'll mark that to be the is leaf, right? Similarly here we want to search, right? We want to search. So int try node root and string key. So again, like it will be right. So for so first of all, let's return false here. If it is not there, so return false. So struct try node star current equals to root for int I equals to 0, I less than key dot size, I plus plus. We'll find the index again. We'll find the index mapping. Index equals to int p of I minus a, and we'll see if card of children of index is equal to null. That means there is no path, so we'll return false. Else card equals to, or otherwise we'll just do card equals to card of children. We'll move to the index. Finally we reach the final node, so we'll check if card of is leaf is true. If card of is leaf, then return true, otherwise return false. So that should do. Let's run this. This is working. Let's try to submit, right? So this is how you can write a try, right? You don't you can do recursively as well. There are two ways, again, like as I said, there are two ways to do this. You can do it recursively or you can do it iteratively, right? So I've done this iteratively because although we generally when we talk about traversing on a tree, we talk about recursions, but here actually we are traversing only on a path, so that's why we can go for an iterative solution, right? So this is how this is how the try works, and this is how we can write the code for a try. I hope it's clear with everyone. Let me know if you have any doubts. Let me know if you have any doubts on this. uh, Otherwise we'll move to the second problem. That is like, it's again a very popular question, and it's a very easy question as well, but I don't want to do DFS here. Like, definitely the solution for this will be, there are multiple solutions. There's BFS, there's DFS, but we want to discuss more about, we want to learn DSU, right? So we want to discuss this solution with respect to DSU. All right. Yes. So the problem is, we are given a grid of size n cross m, right, and consisting of zeros and ones. Find the number of islands. An island is surrounded by water and formed by connecting adjacent lands horizontally or vertically or diagonally, that is in all 8 directions. So basically, we are given a grid of size n cross m, where n is the number of rows, m is the number of columns, and it contains zeros and ones, where zeros are water, ones are land. You have to find what is the number of islands that are there. What is an island? Island is a piece of land that's surrounded by water, right? In all Formed by connecting adjacent lands horizontally, vertically, diagonally, right? So island is surrounded by water and is formed by connecting adjacent lands horizontally, vertically, and diagonally. So we are allowed to move in all 4 directions, right? So for example, here's 0 1 0 1. So how many islands are there? There is one island, right? So this and this together will comprise of island. So there is only one island. So in this case, how many islands are there? See, this one will be one island, and this alone will be a second island, right? So there are two islands. So this way we have to count the number of islands that are there in the grid. So ones means land, zeros means water. As I said, there are multiple ways to solve this. The easiest way will be just to do a DFS on this and quickly figure out like how many islands are there. But we want to learn about DSU. So now, talking about DSU, what exactly DSU is? Let's understand that. Okay, what exactly is DSU, or why do we even need a DSU? So DSU stands for disjoint set union, right? So DSU stands for disjoint set union. Now, as the name suggests, right? Whatever the name is suggesting here, disjoint set union. Again, disjoint means there are two sets, disjoint set. There are two sets that are disjoint. They do not have anything in common. There are two disjoint sets. You are combining them into a single set. So DSU means you have the ability, you have two disjoint sets, you have the ability to combine them into a single set, right? You can combine them into a single set. So that is basically disjoint set union. So whenever you have problems where you break the problem down into something like you have multiple disjoint sets, and in operations you combine two sets together like that, in that case DSU is your go-to data structure, right? Coming to our problem, how is our problem actually DSU? Let's just think about this. So let's think about this like this, that we have a few ones and zeros. 0 1 1 1 0 1 0, right? Now here initially, let's assume each of them to be independent sets, right? Each of them to be independent sets. Now whenever there is a 1 which is adjacent to a 1, either horizontally, vertically, or diagonally, right? If there is a 1 which is adjacent to another one, then we will be unifying them into the same set, because they will be belonging to the same island, right? So we will be, if there is a 1 that is adjacent to another one, they will be belonging to the same island, so we'll be unifying them into a single set, right? So now if we do that, what happens? 1 1, they are adjacent, right? So these two are clubbed together, these two are clubbed together. With this is clubbed together, this is clubbed together. See, these all become a single set. Like once you do the DSU operation, right, you combine them. uh, let's just, I have actually passed across multiple steps. So first step, you will combine these two. Now with these two, you will compare this is actually a valid one, so what we'll do is we'll extend, right, we will extend to these three. Now again, we'll compare with this is also valid, so we'll extend, right, we'll extend. So we'll extend, we'll combine these set to these, like this, right. Again, this is also within, this is also valid, this is also should be combined, so we'll extend, right. So how we'll extend, we'll combine these two sets like this. Finally, this and this again will be also true, so here also we'll extend this and we'll combine all of them into a single set. All of them gets combined into a single set, and that actually forms an island, right, that actually forms an island. Similarly, this is a standalone, this will be a single set in itself, so this will form another island. So the number of sets, finally, what is the number of eventual sets that are available with us? Two of them, because these are combined together, these are combined together, so there are two sets available with us, so the answer will be 2, which is the number of island. So that is how we can reduce this problem into a DSU problem, right? So now let's understand how do we do a DSU. Okay. So initially what we do is, let's consider an example. So let's say we have 5 elements. 1, 2, 3, 4, 5. Initially we'll treat each of them to be independent sets. 1, 2, 3, 4, 5. Let's say we call something like, we have two methods, right? We'll have two methods combine, that will combine two sets, and second method will be find root. What is root? Root is kind of a representative element of a set. So each set will have one representative element that will represent that entire set, so that is the root element, right? So find root. So when we combine 1 2, what it will happen is something like this. 1, let's say 1 becomes the parent of 2, right? 1 becomes the root. So 1 becomes the representative set of this set 1 2. 1 becomes the representative, 1 becomes the representative set, right? Representative element of the set. Let's say we call combine 3 4, right? So we call combine 3 4. So 3 and 4 are combined like this. So 3 becomes the representative element in this case. Okay, so 3 becomes the representative element of this entire set. Now if I call find root for 3, it will give me 3. If I call find root for 4, it will give me 3 as well. Similarly, find root for 2 will give me 1, find root of 1 will give me 1. Let's say we combine 2 and 3. We combine 2 and 3. So in this case, what will happen is, we will just combine 1 and 3, let's say. So now 1 becomes the representative element of this entire set, 1 2 3 4. If we call root of 3, we'll get 1. If we call root of 4, we'll get 1. If we call root of 2, we'll get 1, right? If we combine 5 as well, so 5 is combined like this, and everything comes under a single set, right? So that is how the DSU will work. And actually there is nothing else, right? We are doing it like this. So again, how do we do this? So we actually, in combine method, so there are two methods, right? Combine and find root. Combine, we combine two nodes A and B, and we have find root. Find root will find the root of a node A, right? So combine, in combine we'll first check if, so we'll first find the roots of both the nodes A and B. Let's call them RA and RB. RA equals to find root of A. RA equals to find root of A. RB equals to find root of B, right? RA equals to find root of A, RB equals to find root of B, will get the root of both of the nodes. Now we'll check if RA is equals to RB. That means they're already in the same set. Then we'll just return. Like they're already in the same set, we do not need to combine them, right? Otherwise, what we'll do is, there is an array called parent, right? So that basically in DSU, as we learned, we are storing it something similar to a tree, right? So parent stores the parent element in the DSU tree. So we'll set here parent of RA equals to RB or something like this. Parent of RB equals to RA or something like this. So this is how this combine happens. Find root. Okay, find root, how will find root work? Now find root will check while, so parent, what is the property of this parent? Parent of a node X is parent of X in the set tree, right? And parent of X equals to X for root. For root it will be equals to itself, right? So here we can have a condition while parent of A is not equals to A. While parent of A is not equals to A, we do something additional step, right? Parent of A is equals to parent of A. This technique is called path compression, right? This technique is called path compression. So this is what is called path compression. And A equals to parent of A will move upwards, right? So what exactly, like what happens exactly? Why are we doing actually this? Just think about this. In set we do not care about who is parent of what, right? 1 is parent of 2, 2 is parent of 3, or 1 is parent of 3. We do not care about that, right? As long as they are in the same set, they can be represented by a single element, we are happy with it. So that's why let's say we have a tree like this. Initially the tree that is formed is like this: 1 2 3 4, and we are finding the root of 4. So when we find it, what we see is parent of A is not equals to A. So parent of 4 is 3, it is not equals to 4. So what we do is parent of A equals to parent of A. So parent of 4 will be parent of 4. So parent of 4 is 3, parent of 3 is 2. So parent of 4 will be parent of 2. Parent of 4 will be 2, sorry. So 4 is directly moved here. Now A equals to parent of A, so A moves to 2. So here parent of A is again parent of A is parent of A, but parent of A will be 1 again. So it will remain like this, right? So what are we doing is we are essentially reducing the height of the tree after every find root, right? Because in worst case we might need to travel across the entire height of the tree. So we are reducing the height of the tree by this operation, and by just doing this operation the complexity reduces down to log 2n. Just by doing this the complexity reduces to log 2n, right? So this is kind of like the entire logic, and eventually we'll just return A from here. Like we have reached the root, so we'll return A, right? So that is how the entire DSU works, right? This is kind of the pseudo code for DSU. So let's write the code for our problem. Now in our problem there is actually a problem still, right? So in DSU we are trying to like reference everything in an array, right? So we can definitely maintain a map instead of an array for parent, for maintaining the parent of the nodes. But instead of maintaining a map, what we can do is we can actually give all of our cells some number, right? So how do we number them? Let's understand how can we number each cell. So we want to map all the cells to integers, right? So let's say let's take a small example. So we have 0 here, we have 1 here, we have 2 here, we have 3. So what is the size? 1 2 3 4, right? 4. Number of columns is 4, number of rows is 3, right? When we move to the next column, it will start from 4, right? So the formula will be, just see, the formula will be whatever is the row number into C plus column number. Here the row number is 1. See, 0 1 2 0 1 2 3, right? So row number here is 0, row number and column is also 0. So 0 into C plus 0 is 0. 0 into C, that is 4, plus 1 is 1 2 3. 1 into C, that is 4, plus 0 is 4. 1 into this will be 5. So again 1 into 4 plus 1 1 1, so 5. This is 6 7. Similarly 1 into 4 plus 2 6 and 7. This will be 8. Again 2 into 4 plus 0, 8, 9, 10. So we can easily map them like this, that row into number of columns, total number of columns plus column. This will be the formula for mapping them to integers, right? So so we'll use this, right? uh, so let's create something like a class DSU, right? Class DSU, and here we'll create the parent vector int parent, and here we'll have the public section and DSU, and we'll pass here n size, and parent equals to vector int n for int I equals to 0, I less than n, I plus plus, parent of I equals to I, parent of I equals to I. Initially every node is a parent of itself, because every node is in its own set. So it will be the root of itself, so every node will be the parent of itself, right? For the root node, because they are the root nodes. Now void combine int a int b, will find the roots int ra equals to, also we'll have the find root here, int find root int a, and while a not equals to parent of a, parent of a equals to, will do the path compression, parent of a equals to parent of a, and will return a here. And combine RA is find root, will first find the root of a, similarly RB will find the root of b, then we'll check if RA equals to RB, then we'll just return, otherwise we'll do parent of RA equals to RB, right? Parent of RA equals to RB. So that will be it, right? That will be it. So we have this count islands, right? We have this count island, so we'll create a DSU, and n into m will be the number of cells, n into m will be the number of cells, right? So yep, it will maybe it should let me check, it should be m, right? Like n into 0 to n into m minus 1. So 2, 8, 9, 10, 11, and 4, 3, 12. Yes, it should be n into m. It should be n into m. DSU, and after this what we'll do is yep, for right, for int I equals to 0, I less than n, I plus plus. So we'll try to combine, we'll go through all the nodes one by one. J equals to 0, j less than m, j plus plus, and we'll check if what if is it's a 1, right? If it's a 1, that is if it's a land, ij equals to 1, so we'll move in all the directions, right? So for int dx equals to minus 1, dx less than equal to 1, dx plus plus, like we are moving in all the directions. Dy equals to minus 1, y less than equal to 1, dy plus plus. So next row equals if dx equals to 0 and dy equals to 0, that is it is pointing to the same cell, we'll just continue, right? In this case we'll just continue, otherwise this is how we visit all the cells, like all the cells, that is am I doing in C? Oh, I'm doing in C, right? Sorry, my bad. I'll just copy this part. My bad. Yep, we'll create a here. Okay, we do not need a class DSU then, I think. We can just have this parent node. and we can just have the find root and combine method. We can have the find root and combine methods, and here we can create the parent node. So for int I equals to 0, I less than n into m, I plus plus, parent dot push back I. Right. Now we'll go through all the in this grid we'll go through all the cells. So for int I equals to 0, I equals to 0, I less than n, I plus plus, n and m is not defined here, so let's define that quickly. N equals to grid dot size, int m equals to grid 0 dot size. For int j equals to 0, j less than m, j plus plus. So if you are given movement in all 8 directions, right, so how do you visit all the neighboring cells? You can use this logic that dx equals to -1, dx less than equal to 1, dx plus plus. So basically see, it goes from -1 0 to +1, right? So we are combining all possible values from -1 -1 -1 0 -1 1, like that will combine, right? So for int dy equals to -1, dy less than equal to 1, dy plus plus. So we have all the combinations, but one of them will be leading to the same cell, that is dx equals to 0 and dy equals to 0. So in this case we'll just continue. Otherwise int next cell, next row is I plus dx, int next column is j plus dy, and we can check if it is a valid cell, right? If it is a valid cell, how do we check if it is a valid cell? It will be a valid cell if right, it will be a valid cell if next row is greater than 0, greater than equal to 0, and next column is greater than equal to 0, and next row is less than n, and next column is less than m. It's a valid cell then. So in that case we'll combine what? We'll combine ij, that is, what is ij exactly? It will be, again, we'll use the formula here, uh, m, number of columns, into I plus j, comma, will combine with m into next row plus next column. We'll combine these two, right? So we have done this. Finally it's time to find finally, what's the term, it's time to find how many root nodes are there, right? How many root nodes are there? So we can just in count root, we can do like this, just count root equals to 0. Then for int I equals to 0, I less than n into m, I plus plus. What is the property of a root? It will be parent of I is equals to I. In that case, count root plus plus, and return count root. Okay, return count root. So that should be it. Let's try to compile this, see if this is working. There's some compilation error, might be lot of this is work. Here is the if statement, here this is, here it is, this is also fine, for this also it's fine, for this fine. Where is it? 12. Oh, okay, there is some. Let's run this now. Okay, this is running. Let's actually run our the second sample as well. So that will be Number of rows is 2, number of columns is 1, 2, 3, 4, 5, 6, 7. 7, and the values are 0, 1, 1, 1. So 3, 3, 6, 7, right? 0, 0, 1, 1, 0, 1, 0. So it should give us 2, right? Let's see if this is okay. We are giving 1 here for some reason. Uh, for int, okay, we have not added a condition here that if it is if grid of ij equals to 0, then continue. That should have been one of the conditions. Basically, if it's a 0, then we will not connect, right? Still it's giving us issues. If grid of ij is equals to 0, then continue. Otherwise, go through all the adjacent cells and try to connect them. That's I think is fair. Initially, parent of I is uh, parent of RA is equals to RB. Parent of RA, parent of A is parent of A equals to parent of A, return A. I believe this is okay. Parent dot pushback initially there, okay. I less than M, J equals to 0, J less than M, J plus plus IJ, okay. Let's print their parents as well, right? For int I equals to 0, I less than N, I plus plus, out parent of I, out. So ideally, okay, let's run this. Okay, we have 6, 13, 13. Everything has a parent. 0 has a why is coming here? 6, 13, 13. Okay, yes. 6, 13, 13, 13. That's fine. 13, everything is pointing to 13. Correct. That's not true. And why is everything pointing to 13? 13 is a 0, right? Yep, right. 13 is a 0. 0, 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 is 0. Why is everything pointing to 13? Let's see. Read ij is equals to 0. Also here we have to have a condition, and grid next row next column is equals to 1. Only then you will connect, right? You will connect two of them. Let's run this now. This should solve the problem. I think now it's coming correctly, and our output is 14. Wow. Next column, next row greater than. Okay, let me just break it down into properly into two parts. If next row is greater than equal to 0 and next column is greater than equal to 0 and next row is less than n and next column is less than m, if it is within the bounds. Now here inside, if grid next row, next column is equals to 1, that case we will combine m into I plus j with m into next row plus next column. That's what we should combine. Let's run. And also here also, okay, I understood. Parent of I, and also we have to check here and grid of I. All right. Let's do it like this. For I think it's correct now. Only the answer that we are returning, it's not proper because we are also returning the count of zeros as well. That should not be the case. So for int I equals to 0, I less than n, I plus plus. For int j equals to 0, j less than j plus plus. If grid ij equals to 1, that case int value equals to m into I plus j, and if parent of val equals to val, then count root plus plus. So that should be it. Okay, we are getting a 0 now. Yet what are we doing? Okay, let's actually also print here C out. I j parent of uh, m into I plus j. So the first example was okay. There were a few ones. Next row is I plus dx. Next column is j plus dy. Also, if grid ij is equals to 0, in that case continue. Otherwise, dx dx minus 1, dx less than equal to 1 plus plus, dy minus 1 less than equal to 1 plus plus, dx equals to 0 and dy equals to 0. That is continue. Otherwise, I plus dx j plus dy if next row greater than equal to 0 and next column greater than equal to 0 and next row less than n, should be less than n, next column should be less than m. Yes, only if this is true. Yes, that case if grid of next row next column equals to 1, that is it's a, does it never come here out here? That's weird. Should come here, right? Out I j next row column. I think I have messed up my loops here. Bit. Okay, so we have I 0001 0010. That's true. 0011 also fine. So 0110 01, we have 110 is 0110 is true. So zero, sorry, we have 0 1 1 0 0 0 1 1 0 after that. Okay, so 0 1 1 0 should be 1. That's interesting. Grid of next row. Okay, it is equals to, it's a character. It's a character here. Here also it should be a character. Sorry, it's a character, so it should be 1 like this. Here also it should be this. Here it should be. Now it should work fine. I think it should work fine. That's statement coming. Move this and against custom file and run. So this is working. Let's try to submit this. Yep. So this is also working. So that's about DSU, like how we can use DSU, or what is the use case for DSU, right? So DSU again, like DSU means whenever you have to combine, you have a few disjoint sets and you want to combine them together. So in that case, DSU is helpful. So that brings us to the end of today's session, and also it brings us to the end of Amazon in 29 days series. About the next, like what will I be doing next, I'm not sure. So definitely will be updated much before, like whenever something else starts, I'll be definitely updating you. But for now, I'll be taking a few days of break definitely. So yeah, like just keep on practicing, right? And yeah, like just practice, and if you have not solved some problems, make sure you solve them whichever I've given, because all of them are very very important. And also make sure to recapitulate on all the concepts that I've covered, mostly around DP graphs and these things. uh, so yeah, so thank you guys for joining in, and I'll be seeing you soon.